normally.
Okay, so our topic is the sum of squares, which is basically saying something like a squared plus b squared, right? Sum of squares. So what we focused on was Pythagorean triples and how to find different Pythagorean triples such that a squared b squared equals c squared. Okay? So now when you have to find triples, or you want to try to find any distinguishing triples, you find the difference between b and c. We know this has a lot to do with it because that's what a squared does. It's the difference between b squared and c squared, right? Okay. So if you take, I sort of developed this triangle method, which goes like this. So the what we call the zero row, which is just all the counting numbers squared, like 0, 1, 4, 9, 16, 25.
There is a comparison. You might want to move somewhere where you should go sit, but not able to sit from where you sit.
Okay. And then row 1 is the difference between these first two numbers, which makes little triangles. And then row 2, etc. And then this we also add in the next row. Since this number would not be 68, it'd be 68 minus 17. Because any number here, you're just making this little diagonal part like this. So 32 is between 49 and 81. Okay? So if you can find two numbers, if you can find any number in any of these rows, rows 1.
So the first is the squares, so the second line is the difference between the squares. You can check the squares?
Yeah. And
And
third
the
is
third line
between two
is the
squares.
sum,
It's a sum of all the difference.
the sum of difference.
Which means it's the difference between the squares of the two. So if you find any square number in rows 1 to infinity, then that will be part of your triple. Right? Okay. So we try to find how to find patterns in different rows. So in what we can find by define by definition in a triangle is that this side is A and this side is A.
Zack, he's implying we can
Oh, okay, fine. I have to do here.
translate.
Okay. So we have a triangle. Sean, you want to try this because I can't draw.
Triangle?
Yeah, I draw a triangle. Okay. So on the sides, this side is going to be A. This side is A squared plus x squared over 2x.
You're in the way of the camera, guys.
Okay. And this one is A squared minus x squared over 2x. And by definition, any right triangle will have these measurements where A is this the shortest side, or actually it's the difference side as we define it, number that's in here, and then x is the difference between the shortest, between the second longest and the hypotenuse. So when we find this, we can find that in the first row. You will find squares. This is just another different pattern we found. The squares will happen on the 4th, and then because row 1, you take I'm trying to look at this. So okay, so in row 1 you have all the odd numbers except for 1, but you have all the odd numbers, counting numbers, right? Because you're just adding 2. Oh, what you do? Yeah.
And Sean.
Yeah, Sean.
So basically this is a Pythagorean triple, and these are two consecutive squares, n squared and n plus 1 squared. And if the difference of these squares, n plus 1 squared minus n squared, is a square number, then it's part of this Pythagorean triple. And this simplifies out to become 2n plus 1, which is basically row 1, all of row 1. So basically every number in row 1 is part of the Pythagorean triple.
So how do you do it? Say if you pick a number in row 1, say 17, what is it?
So if you have 17, so 17 would be 2 2n plus 1. And in this case, n would be 8. So an n squared would be 64. N plus 1 squared would be 81.
And so let's say Pythagorean triplet, 64 and 81.
Yes. No, it's not. No, the root of this number.
Yeah.
So
So
what-
it's,
sorry.
it's only if these are squares.
So you find an
So
R
what you just did, what does give that Pythagorean triplet? What?
No, it's saying, it's saying root 17, root 64 and root 81
No.
are triple.
No.
Yes.
Yes.
Root 7 is the thing.
That's these are the squares. You're adding the
So
squares.
if you want a triple with 17 in it, then you would square 17. And then subtract 1 from that square, divide by 2, do the same thing.
Okay. You need a calculator?
It's 280.
29.
It might not be even numbers. It might not be nice numbers.
But I'm gently inclined, you got to go slow and not because people can do that stuff in their head, know their head and say, yeah, you're right.
Okay.
No clue if you're right. Here you go, John.
Yeah, what is it?
144 equals 12.
It's like you had the Pythagorean triple of root 17, root 8, 64, and root 81, right? So that one has 8 in it. So the Pythagorean triple is going to have n in it. So you're trying to like make,
I don't know why you're squaring it. Why are you guys squaring it?
Because
because then what you come out with, you can take the square root of that and that's what you
like
do. You
it's
can also
the
just multiply it
17.
by 2 and add 1. And then
And so what you say?
So the difference between 145 squared and 144 squared is equal to 289,
Yes.
which is the square of 17.
So what kind of Pythagorean triplet do we get? Straight up the Pythagorean triplet you got this one.
Now you're getting
17,
Yes.
144,
Yeah.
and 145.
That's it. Big number.
They are
Oh, wait, then why do you square 17 as well?
because when you
Yeah.
square, that's going to be part of Pythagorean triple.
Yeah.
Hard to say precisely what you're trying to say. So let's take one more time. People are almost there. So try to find a way of saying it so people can follow.
So for any odd, if you have any odd natural number,
Yes.
any odd natural number is part of a Pythagorean triple
Yes.
because of this rule. Because any odd natural number is always can be expressed as 2n plus 1 with n natural numbers.
Yes. And what does it do? Oh, all the way through. So how do you create this
So,
people?
So what he's doing is he's just taking that number, and what we did is we tried dividing it, and then over more, so we tried multiplying it. If it was a square, you can do this method, and if it's just any other number, you can do this method.
since 17 is not a square, you can't do this method because
Yeah.
it wouldn't be part of it. But
Yeah.
say you have 9, which is a square, you can use this method and then
What is
find
it
out
gonna do?
what.
Do it. What is it gonna do?
So 9 equals 2n plus 1. N would be 4. N squared would be 16. And n plus 1 squared would be 25.
And the triple you get?
Would be,
It would be 9, 16, 25, or 3, 4, 5.
3, 4, 5.
what do you want to say?
I just have a comment
Okay.
about that. So basically, like, I think what they're doing is they're just extending that row. They're just going
Yeah,
until they
so-
hit 17 squared. And once
Yeah.
they hit 17 squared, they can see the two numbers that are.
Very good.
Yeah.
Very good.
Okay. Now also, so that's like the row 1.
How many people follow so far? That was not an easy thing to follow. No?
So from this, we thought we had all the Pythagorean triples that exist covered, but then by some strange coincidence, we found that 8, 15, 17 is a triple. And it does not conform to this rule that the last two numbers are not 1 apart, but they're 2 apart.
And this is because you can find numbers in the second row that have a difference of 2. And because this is true, because any number in row 2 is going to be, it's going to be 2, it's 2 squared Yeah, you would it's two, that'd be 2 squared, okay, 2 squared, plus, 4 plus, 4 times 2 plus x. That's,
No, what is that?
that's wrong, sorry, that's my translator.
What is that?
That's,
What are you trying to do?
right now we're just showing numbers in the second graph.
Steve,
Oh,
the numbers in the second row are just the differences between their corresponding squares.
right, and the difference between each of these will be 4, because the difference between these are 2, and it's just 2 plus 2.
So if a number in row 2 is a square, like 16, the other, it would be part of a Pythagorean triple. And since all these numbers are multiples of 4, we're saying that all squares that are also multiples of 4 are part of a Pythagorean triple.
Give an example.
So since like 8 is multiple of 4, so a squared 64 is also multiple of 4. That is an example of triple that can be set rule, where the two bigger numbers are squared.
A little one more time. But these things are low.
A squared 64, which is also a multiple of 4, so it'll be in the row 2. And it's the other two numbers in the triple, which are 2 apart, are going to be the two numbers that are up in row 0. That is the difference of. So let's just find triples like that.
60, what is 64?
64 is, yeah.
All you know is going to be 15 squared and 17 squared.
You already knew that was a triple.
I know, that's how you're trying to show what you're doing.
Well, it works because if you use this method,
Okay.
yeah.
You don't exactly use that method. So if we have a number in row 2 that is a square, then, and if we call it n, then the other two numbers that correspond to it would be n over 4 minus 1 squared, and n over 4 plus 1 squared.
Wow. And the third number is n squared, yes.
Yeah.
Right, and we can establish that because of this rule.
N
because-
squared or n?
No, it's n.
Huh?
Yeah, and we can establish that because of this rule, because say that we're in the second row, that's going to be a squared plus, let's say, second row, 4 over 4. So we know that it has to be a squared divided by 4.
Do you already know which one of them is going to be the largest, and which one is going to be the
You should
smallest?
get rid of the squares on all of them if you're gonna get rid of them.
Well, I guess.
No.
No.
I mean, either square them all or square none of them, otherwise it doesn't
Yeah.
make sense.
But isn't it squared?
What? No.
And-
And if we,
It is.
the root of
The
n is
Pythagorean triple is without any of the squares. I mean, when you put the square, you're showing that the sum of the first is equal to the third.
So you're saying the triplet is n over 4 minus 1, n over 4 plus?
Yes.
Yes.
well, that's the squares of the, I guess.
Right.
And so that allows you to find the Pythagorean triplets where two numbers are 2 apart?
Yes, and you can find as many as you want because according to this rule, that it has to be, that n is divisible by 4. And that
So could you create us a Pythagorean triplet where numbers are 5 apart?
5 apart. Well, what you would do, you say, no, I'll start this. A squared
How many people are still following, by the way?
minus 25
I've never seen anything like that.
over 10.
I've never seen this kind of approach to it.
Okay, so now that means that a squared has to be divisible by, it has to be something 0.5. So a squared can't not be divisible by 2, but it must be divisible by 5.
I don't understand.
So, because according to this rule, we're just translating that into this, right? Right?
Yeah.
Okay, so now any, in order for it to be squared, or any,
Just do it.
okay,
So we want to Pythagorean triplet where two numbers are 5 apart. Does your method work or not? Does it?
we don't have a fully working method yet. We can't find them all.
You seem to have it. You just seem not to realize what it does, but you seem to have it. That's what's so exciting.
Well, right now, what I found is that a squared has to be a multiple of x. And for that to be true, that means that in row x, then a has to be a multiple of root x. So,
What would your row 3 look like?
row 3?
0, 1, 2, what row 3 look like?
Row 3 will be 13. No, sorry. Let me say 16. It's 16. I'm not a good counter, I'm sorry. 15, 21,
See, there's a pattern
26,
here too.
It's,
21,
it's plus 6.
6
6,
apart every time.
31.
Oh,
It's 6 apart.
yeah.
It's because you're just adding the 2. Okay. So now, a way that I sort of denoted, this is a little bit confusing because I didn't get this full answer myself. I couldn't fully figure it out. But because for any number in this row, for instance, it's going to be in row 3, it'll be 6x plus 15, right?
So if any one of these row 3 numbers is a square, that means
Say it again, say it again.
if any number of these is a square, it is also part of a Pythagorean triple.
And if
Where
not,
is-
it's not.
No.
Well,
Um,
but all of these.
What we know, any number in this row is going to be 15 plus whatever row it is, plus 2 times any other number, right? Yeah.
So basically, if you want to Pythagorean triple where 2 of the numbers are n of 5, you look for in the nth row,
Yeah.
and then row, and you look in row n and look for square.
Not
That's
only row
what it
n,
would
though.
be to look for patterns.
Any
within
row
the system.
that is a multiple time.
See, all of the numbers in row 3 are just 3 times numbers in row 1.
Yeah.
So
And so
we
one number to row 5 would be
would be
multiples of row 1?
not necessarily.
Okay.
We haven't done that yet.
So in row 5, the starting number here is going to be 35, and it's going to be adding 10 for each one. So 35 plus 10, so it's like 35, 45, 55, etc.
Multiples of 5.
Multiples of 5, right? Exactly. So
Wait, but then it's not.
that means that A must be multiple of 5 as well.
Why?
Yeah.
When you said first number about 5, what?
First number in row 5 will be 35.
What do you mean, 25?
No, it'll be 35.
How is it? But wouldn't it be a difference between 0 and 25?
Difference what?
That would
Yeah.
be, wouldn't that be row
30? Row 5 is 35.
Yeah, it would
Zach,
be 25.
Zach.
Zach, it would be 25.
It would be 25 and 0.
Speak.
Zach, wait, you said the difference between the two was.
No. This row is not actual in existence. This is just theoretical. No, it
Listen to me for a
That's
second.
correct.
Yes, ma'am.
Wait, so, what you're saying that, so that row right there was 6 apart for each one, right?
Yeah,
And
this
you're
will be
saying the
8
next
apart.
one will be 10 apart?
8 apart, and no, row 5 is 10
Oh,
apart.
okay.
Row 5 starts with 35.
35, 4 apart, 6 apart,
8 apart, 10 apart, 12 apart. Because you're always just adding another 2 apart. That's one you're adding. Right? So that's up to 35, right? It goes 35, 45. So any A where A is a multiple of 5, then, sorry, where root A is a multiple of 5, then A will be a square. So like,
35.
because 5 is already in use, you can go,
So, Sean, what kind of triangle do you have?
But
1, 35, 36, what kind of triangle do you have?
if 35 were a square, then that means it would be a Pythagorean.
Oh, you mean 35 is a...
Yeah.
right. So because this will be every other multiple of 5, because it won't weigh into 2 and 0, and 5 squares are already used, so you have to go then to 15 squared, which gives you 25. And that'll be the first square in row 5. And then the next one will be
It's pretty
625.
interesting what you did, though. It's not that obvious to see, but Matt can help in some way you, because they're saying the same thing. They're saying if you can write it in the first row, then you can write it in the fifth row, it's multiple. Their method connects the way of creating it for multiples of the same natural number, particular kind of multiple. Okay, I want to finish that. Okay.
Wait,
what else?
35?
So 35 would not work because 7 didn't work.
Wait, 35? No.
Wait,
30?
Yes.
Are you saying?
Can I explain why it can't be 35?
But it is 35.
But isn't the one before 29?
What that, oh, that's 24.
Okay, never mind. That makes sense.
Wait, are you saying the 35 cannot be at all part of the criteria of people who are saying something else?
No, we're just saying that's just how that row starts. That row starts with the 35. It's right about there. I haven't done that.
I guess if a number ends in, a square ends in 5, it's part of a Pythagorean triple like that.
There would also be a comment.
225.
Especially like that.
625.
25.
Yeah, 225. So it would be part of some Pythagorean triple.
Alright, keep going.
Okay.
What else?
So, in the first row, the first square is the fourth one. The second square is going to end up being the 12th one.
What do you mean?
In the
row.
row, the 12th one, and then the next one will be I believe the 20th one. The idea is that you add, no, the 24th one, sorry. The idea is that you add 8. Because all the squares in here will be 1, which isn't actually right, 1, 9, 25, 49, 81, it's just the odd number squared, right? And the difference between each of those is either 8, then 16, and then 24. And then you take that difference and you divide by 2. So, the difference between, so like for 25, you know that 49 will end up being the 9 is the 4th. So then you have 32, so 32 over 2 is 16. So it'll be the 20th. So the 20th number here will be 49.
That's,
Wait, what?
So that means that the 4th, the 8th, the 12th, the 20th,
What are they, 24?
the 20, something like that. There's a pattern there. I can't simplify it yet, but does anybody else see what I'm saying there?
I see. Wouldn't 49 be the 24th?
Yes. It would be the 24th. Yes, sorry. Yes. Sorry. But
Alright guys, what else? Is there any more?
so when you're you want to
Sure, so,
You might want to erase a little bit of the board so we can write.
you want to
Whatever we
I'll
want.
figure this.
Whatever we want.
Figure it some other rows.
how about this?
Oh no, yeah, you said.
Can you?
So if we have any Pythagorean triple, if we have it like A, B, and C, we know A squared plus B squared equals C squared. And we only needed to find triples like this where these were all relatively prime. Because if they weren't, what we could do is we could take we call it base triple, where these are all relatively prime, and we can multiply it by like a coefficient k or something, any constant, and then it would still fulfill the requirements. And we can show this with the distributive property. If you multiply both sides by k squared, a squared, k squared, b squared times k squared equals c squared times k squared. And then you have a new Pythagorean triple that's AK, BK, and CK.
Do they all have to be relatively prime, or do they just not all have to share a common factor?
They all have to not share a common factor.
The GCF.
Like two of them
GCF
can.
The GCF of all three.
Oh, do we see that it cannot be that 2 of them do and the third one doesn't? Do we see that as well?
Oh, yeah.
Okay. I think that's what they will ask. Okay.
They're all of them.
Yeah.
All of them.
So we're trying to work on finding as many like bases as possible. Like we know that there are bases with difference of 1 and 2, but we don't know about any others so far. Thus far, we're a little bit confused about that. So we looked at where A is a multiple of another number, and A is another prime number itself, because we're counting 1 as sort of a prime number in this case, because it's not so many factors. So where A is a multiple of a number, we can make this really cool chart. Someone else can write this on. Erase this chart. So if you just make like a chart of like 1, 2, 3, 4, 5, dot, dot, dot. So the idea is that in what I'm trying to find conjecture of is that in a certain, for a certain A where A is a multiple of something, there are only a certain number of rows that it could ever work in.
Oh, say it again?
I'm trying to find a certain A in one of these rows, like a certain A that A is a multiple of a number, let's say number B. And for that, there can only be a certain number, only certain rows can ever have a square that will have a multiple of B squared. So, yeah, now I can make a side column of 1, 3, 8, 15, 24. It's basically just these numbers. Now, if this number is 1, 2, 3, 4, 5, 6, one of those numbers is a factor of this number, then you can find a square of it in that column event, in that row eventually. But if it's not, then you can never find one. So, if you start making check marks that they're factors, just like obviously a factor of them all. Yeah, 3, 4, and 5. Okay. But especially if you look at 3, for instance, it won't be 8, it will be 15, it will be 24. And then
Wait, what are you guys?
this number is a factor of this number.
Okay.
Okay?
Wait, and
So,
then
because the difference between these numbers becomes 5, 7, 9, 13, and 11, 13. If you look at the 3 row, which is the one I was basing it on, it started
You're
at,
saying that 24 squared would be, you can see 24 squared in many rows. In a row which has any of those.
you can see, no, I'm saying you can see a multiple of any of these numbers in this row, eventually, thus far.
wait,
There has to be a square number that has one of these as one of its multiples of its base in the 4th row, in the row that starts at 24. So if you look at the 3rd row, what you'll see is that it goes check, blank, check, check. This one's going to be blank, check, check, check. That's because when you're adding, every 3rd one you add a multiple of 3. You're adding all the odd numbers, and the first 2 you don't. So it goes check, blank, check, check, blank, check, blank, check, check. And that's just a pattern. And then, for instance, 5, you'll have to see it. You'll see it here, then you won't see it. You'll see it here, you'll see it again. Then you won't see it for 2 more. Then you'll see it again, you won't see it, then you'll see it for 2 more. And it's cool to see the patterns, and that can help you sort of narrow down numbers to give you an idea. So, yeah, that's a cool thing. Think of that. Anything else you guys want to add? Okay.
This is a big question, so do you guys intend to continue or you stop or what?
I'd like to continue. I like this.
It's interesting.
Yeah.
I would say that much. I mean, you probably need computer program to just generate the data, so you can have,
Yeah.
right? The same way as Danny and Andy generated the Pythagorean image they want, right? But I haven't seen people approaching the way you do. I like what you do, and it's a hunch. I don't see it all the way through, but there's some intuition behind it, and I think you should be, in the very least, you should be able to create any Pythagorean triplet. So you should be able to pick any number
Okay.
and know if it's going to work or not. And the question is, so simple question I would ask you now, right? I would ask you, so if I take any odd number, is there some odd numbers which cannot be at all in any position? Parts of the Pythagorean triplets. So it's true that if I have 7, I cannot have a Pythagorean, I cannot have a Pythagorean triplet with the number 7 in it. Can I? Can I not? Always.
You can always.
Huh?
You can always.
You can always.
And you can just keep drawing up the thing until you
Because
get
as, yeah, as we established,
Because
any
all
number
numbers
is
squared,
square.
all numbers, all our numbers are gonna be in the
Square any odd
So-
number.
one doesn't work.
Wait, so you're saying that for every odd number there would be a Pythagorean triplet which would have.
Yes. And one does work, one
One
zero.
does.
1, 0, 1.
1, 0, 1.
One, zero, one.
Triangle.
But there was triple. So,
Nothing.
There you go.
Oh, wait.
it
I think it's good where because we can
Nothing.
create that.
Oh, yeah, but it's one
And then I started, this is not really possible to draw a graph. This is just a sort of example of the 5 multiples. As you see, it makes this little chart, and only in these little graph brackets, every other with 5, you can find numbers that never could possibly
1
be a
squared
multiple.
plus 3 times squared.
And I
This, so you guys done?
yeah.
Very good job. I mean, not finished, but very good.
1
Very good.
squared plus 1 and a third. 1 and 2 squared.
For people who are interested in it,
It's a 3, 4, 5, 6, you can't find
I want
one.
1, I just did.
for people who are interested in it, it's amazing that the super amazing thing is how human intuition works. How do people know what's important, what's not important? There's a friend of mine who many of you might have a chat. Yeah, don't. Yeah.